What I love about programming is how you can just use a few basic commands to make a computer do whatever it is that you want. Whatever you can come up with is possible when you puzzle the right pieces together. I personally get inspired by the beautiful patterns in the real world and how I can use these basic commands to mimic all of that beauty. I am Sam, and today I want to take you with me as I try to understand and program what it is that make waves behave the way they do. And in the end I hope to get something like this. I will get there by starting from mathematics, because those smart mathematicians already figured out all of that. But I don't blindly want to implement some random formulas, I really want to understand what it all means. So that with that understanding about how waves work, I will be able to create waves, whether it's in some game engine, Python code, or even punch cards. So if that's something you're into, you're in the right place. As I said, I will start from mathematics, and when you Google the equation to describe a wave, you will most likely end up on the Wikipedia page of the differential wave equation. As the name already suggests, this equation uses derivatives. Derivatives can be a complex mathematical topic, but it really does not have to be. If you already understand the main ideas, it becomes a lot less scary. I will give a short example to explain you these ideas, but I won't go into the complex mathematical notations or anything. And if you already are a math wizard, you can just skip this part. So, let's say we have a function that describes something. Like, for example, let's make a function that describes the distance traveled over time by a car. That car would first have to leave its home and drive a bit on local roads. So his travel distance doesn't increase that fast in the beginning. Then the car drives onto a highway and his distance increases much faster. And after a while of driving here, he takes an exit and drives more slowly to the destination. In that case, this would be the graph describing his travel distance over time. This graph is a mathematical function that describes the position of the car as a function of the time that has passed. The only thing a derivative is the slope of this function. Or in other words, the only thing a derivative is a value of how quickly the value of a function increases or decreases. We can add a second graph to show this derivative, and that would look something like this. So, the derivative of a function is a new function that describes the rate of change of another function. So in this example of the car, what do we call the value of how fast the travel distance changes over time? Exactly, we call that the velocity. So the derivative of the function describing the travel distance of this car is the velocity. And why stop there? What happens if we take the derivative of this function again? A derivative of the function describing the velocity would give us a third function, describing how fast the velocity changes. And in our little example here, that would look something like this. And what do we call a value indicating how fast velocity changes? Of course, that is acceleration. So while velocity was the derivative of distance, acceleration is the derivative of velocity. And because taking two derivatives of the traveled distance gave us the acceleration of our car, we call the acceleration function the second derivative of the traveled distance. We could also take the derivative of this acceleration again. That way we would get a function showing how quickly our acceleration changes. And that would then be the third derivative of our initial function. But in this case, that doesn't have a specific name, I guess. And let's have a quick look of what this looks like when written as an equation. When we go to the Wikipedia page of the equation of motion, we will find them under the kinematic equation. And there they are. So the displacement is shown as the letter r, and we see that the velocity v equals the change of displacement over time. Also, the acceleration is the derivative of velocity, or the second derivative of displacement. And all of that is written down like this. Now that you have a basic understanding of what differentials are, let's apply it on the example of the wave equation. First, we need to understand what we are dealing with. So what do we actually want to know with our wave equation? We start from a given surface of small particles that are connected to each other. All these particles have a certain displacement that make up the shape of our surface. And we want to know if the surface has a certain shape, how will the shape be 1 second from now? And what would it look like in 2 seconds? And 3 seconds? And so on. And that is exactly what the wave equation will tell us. It will tell us how displacement of these particles changes according to the shape of the surface. And if you can calculate what the surface will look like in 1, 2, 3 seconds, we have everything we need to simulate the entire surface for any given amount of time. When we go back to Wikipedia, there is an overwhelming amount of information here. But this first formula you see is what you should focus on. Just like we saw how the kinematic equation of our first example was written down, this is how the wave equation is defined. Okay, that's a lot of maths. But let's slowly dissect all the symbols so we can translate it to normal English. There are a few letters we need to identify. First there is the letter U, and this letter is the displacement of our particle. Then there is a letter T, and T stands for time. C is just some constant, a fixed non-negative real coefficient. And the last letter is the letter X. That indicates a spatial dimension. You also see X1, X2 up until Xn. That just indicates there can be more than one spatial dimension in your wave. We will only work with 2 spatial dimensions, not 3. Our displacement is not necessarily a third dimension, but it's a variable on its own. So we will work in 2 dimensions. On the left side of the equation, it says the second derivative of u over time. So the second derivative of the displacement in function of time. But wait, we already saw this. This is actually the same as our previous example, where we calculated the second derivative of the traveled distance of our car. This was our acceleration. So whatever this function calculates, it is the same as the acceleration each particle experiences. Then we just have to figure out what it is on the right side of the equation. So we just have a constant c multiplied by something that looks similar. Here we don't have the second derivative of displacement over time, but the second derivative of displacement over a spatial dimension. And that we sum for each spatial dimension there is. But what does this mean? The second derivative of displacement over a spatial dimension. Let's first understand the first derivative. If we calculate the first derivative, we get a value that represents how quickly the displacement changes as you change your location. In other words, that is just the physical slope of our surface. If we take a second derivative, we will find how quickly the slope changes on our surface. This is the curvature. If this value is high, the slope changes rapidly and the surface is very curved. When the value is negative, the surface curves as well, but in the other direction. And when it is 0, the slope stays the same. So it's just a flat surface with a constant slope. And when we put all of this together, we get the simple concept stating that the acceleration of each particle is proportional to the curvature of the surface. That's it. That's what the wave equation means. The acceleration of each particle is proportional to the curvature of the surface. And now that we understand this concept, it's a lot easier to program this in some sort of visualization. I will use P5 for implementing this, but you could use any programming language you like. Now you know the basic rule, that the acceleration of each particle is proportional to the curvature of the surface, and you should be able to program it any way you like. But if you want to see it first, I'll show you how you can do it. P5 is a great visual library for JavaScript. If you want more information on how to use it, I highly suggest you watch The Coding Train on YouTube. He has an endless amount of videos covering almost everything P5 has to offer. The first thing I will do is create our environment, our surface of particles. I will add a variable to determine the resolution of our surface, and a grid of 100 by 100 particles should do. Then I need to make 3 lists to store the values for displacement, speed and acceleration for each particle. I will give each particle a default displacement of 0.2, and then I will visualize these values with a color scale where black is 0 and white is 1. Although we are working with a grid of particles, it is a lot simpler to just have all the values in one long array. So the 101st item in this list would actually be the first particle of the second row. So to determine the position of a particle in the array, you just have to multiply the row of that particle with the amount of particles in a row, and then add the horizontal position of that particle. Because we will do that a lot, I will put this calculation in a function, so we don't have to write it every time. I will also create an image to show all these particles, and then each frame of our animation, I will update the pixel values of this image. In the setup function, I will just do a basic setup, and if everything goes right, we now have a flat surface. Then we have to set up a loop so that every frame the image is updated according to the values of our particles. So in the draw function, I simply loop over the pixels of the image and update it according to the value in the array. Also for updating these pixels, I will write a function to keep our draw function easier to read. And then at the end of our loop, I have to make sure the pixels are updated and that the image is shown on our canvas. Then there are 2 more things I want to do. First, I want to be able to click on the image and have the surface be disturbed, so that we can start some waves that way. And then second, we actually still need to implement our wave equation. But let's first do the mouse click. So whenever the mouse is clicked, I want to have the X and Y location and figure out which particle was pressed. And then I want to change the displacement of a number of particles within that region. Let's say I want these particles moved by a distance of 5. And then I loop over all the particles that are potentially within range and change their displacement values. I will reduce the amount of displacement as it gets further away to get a more natural look. And now when we click on the image, we should get white spots where we disturb the surface. And that seems to be working just fine. The only thing that's left now is to make the actual magic happen and have the values of our particles change over time. So in every frame, we have to calculate what acceleration our particle should be, and with that acceleration, we can update the current speed of our particle, and with that speed we can determine what the new displacement should be. So before updating the pixels of our image, we will loop through our grid of particles. You may have noticed, but I also did this when we updated the pixels of our image. I actually will skip all the particles at the edge, because we can't calculate proper slopes of them. And leaving them at 0 will give us actually boundaries that reflect the waves we create. So it's no real use to loop through them anyway. Our equation said that the acceleration is proportional to the curvature of the surface. And to get this curvature, we will certainly need the values of all the adjacent particles. So I will get their indexes already. And then for each spatial direction, we will calculate the curvature by seeing how the slope changes. And when we add these together and multiply it with a constant, just like the formula said, we find the acceleration of our particle. You can play around with the value of c, but a value of 500 gave me something that looks nice. The speed of our particle changes with the acceleration multiplied by the time between each frame, so let's calculate that real quickly. And then we have to update our value based on the speed we calculated. But we must be careful. If we update our value at this point, our next particle will use this new value rather than the previous one, and that will give strange results. So instead of updating all the values at this point, we will store the newly calculated values in a new list, and when we have calculated all of them, we can update all the values at once. And this should be all, so let's see if it's working properly. And ta-da! Isn't this exciting? We simulated this wave behavior, but it does get messy after some time. So if you want to solve this, we can add a dampening factor that slowly reduces the speed. And now our waves will slowly lose their intensity. And that's how you implement the differential wave equation in whatever code you like. I also played around with coding all of this in Blender using Python, and that code looks something like this. So the structure is mainly the same, but instead of changing the colors of an image, I changed the location of all these vertices. I also had to make some adaptations because the particles here are not in a nice grid, but when you stick to the concept that acceleration is proportional to the curvature of the surface, anything is possible. So I hope you found what you were looking for. If you have any questions about this or you think I made a mistake, please let me know so we can figure it out. And besides that, I'm really curious to see how you would implement this in a project, or if you managed to create a visualization like this on your own. Good luck!